Well, good afternoon. What I'd like to talk about today is photochemical smog. We'll talk actually less about controlling it, more about what it is. In terms of controlling it, we'll look at what is it that in terms of the chemicals that we need to control. In the last third of the course, we will focus extensively on treatment technologies, where we will talk about how do we control these specific pollutants that cause photochemical smog. So just to make sure that we're all on the same page in terms of ozone, when we talk about ozone, we talk about tropospheric ozone. So we're talking about ozone in the atmosphere close to ground surface. And then we also talk about stratospheric ozone. So we're talking about ozone in the stratosphere. Today, we're talking about tropospheric ozone. Refer to that as bad. Explain why. And stratospheric ozone, that is the ozone that we've talked about in terms of protecting and mitigating UV radiation. We'll talk about that actually next week and the whole issue with ozone depletion. So when we talk about ozone depletion, we're talking about stratospheric ozone. When we're talking about ozone as being harmful to human health and the environment, we're typically talking about tropospheric ozone. So the reason ozone is problematic, it is a strong oxidant. Because it is such a strong oxidant, as we talked about early on, it reacts with the cells in the mucous membrane. It reacts with the cells in the bronchi, and actually, if it makes it all the way down into the alveoli, with the cells in the alveoli. It causes shortness of breath and pain when taking a deep breath. It inflames and damages the airways. It also aggravates lung disease, such as asthma, emphysema, chronic bronchitis, and it can make the lungs more susceptible to infection. In terms of the effect, we often, in the summertime, you'll hear the term ozone alert. These are days where there are high concentrations of ozone in the troposphere. And we can look at this in terms of lost working days. So these are the number of days that are lost because of health effects related to ozone. And this is data for 2010, which was the most recent data that I could obtain. We're talking about, in the US alone, about 1.24 billion lost working days. We also can talk about asthma symptom days. And if we look at this for children ages 5 to 19, we're talking about roughly 118 million days. So that's the number of days that asthma is aggravated because of ozone times the number of children that are affected. So you can see this is very significant. And as a result, ozone is a regulated pollutant under the Clean Air Act. So we do have a national ambient air enact the National Ambient Air Quality Standard. Sorry. Ozone also affects vegetation. It leads to reduced growth, reduced survivability of tree seedlings, also various different plants. The images that you see here are all caused by ozone in the air surrounding these plants. So you can see, actually, we talked about chlorosis, loss of chloroform. You also see chlorophyll, the loss of chlorophyll, and you see that here also. In terms of the impact in the US, the result of ozone impacting vegetation is considered to be greater than about $1 billion US per year. So that's the loss in income from the impact of ozone on agricultural and commercial forest yields. In China, and the data from China is from 2014, and it's estimated there to be somewhere between 1.6 to 2.2 billion, equivalent of US dollars. Sorry, trillion dollars per year. So talking about an order of magnitude actually greater, or 3 orders of magnitude greater than in the US. So roughly about $1 billion loss in the US per year. We're talking about $2 trillion per year in China. This is just one set of data for the ozone air quality index. We use this term air quality index because it allows us to compare the level of pollution across multiple different pollutants. So we can compare, and you can see it here, we have ozone, PM2.5, these levels for PM10. We can look at NO2 levels, we can look at SO2 levels, and we can relate the impact, essentially, of these pollutants to one another using this air quality index. And the color coding that we use is from green to a maroon color. And you can see it here, where you can see, for the most part, most of the East Coast doesn't have any coloration. So on August 17th, 2020, the levels of ozone were all acceptable in most of the eastern part of the US. You can see that in much of the Southwest, you see that there are significant concentrations of ozone. So the yellow is for moderate. Now we can relate these to ozone concentrations. So when we relate these to ozone concentrations, we're talking about concentrations between 51 and 70 parts per billion. Less than 51, less than or equal to 50 parts per billion is considered good. If we look at unhealthy, we're looking at 71 to 85 parts per billion. That's unhealthy for sensitive groups. We're talking about, they're looking at groups that are immune compromised, groups that have asthma, COPD, other respiratory disease, also groups that have cardiac illness because of the impact of the pollutants on the cardiac system. Unhealthy, we're looking at 86 to 105. Very unhealthy, we're looking at 106 to 200, and greater than 200, we're talking about hazardous. So the 0 to 50, the 51 to 100, those are consistent for the air quality index. These levels vary with the pollutant. So these are specific for ozone. If we looked at PM 2.5, for instance, we would see a different benchmark for each of these levels. Now, what I'd like to do is we're going to look at the ozone levels on a particular day in Southern California. So basically what I've got is we're going to look from west to east, and we'll look at a number of monitoring stations. Notice we have mountains to the east of Azusa and Banning, and actually to the east of all of these 5 locations. And what we want to look at is how does the ozone levels change with time of day? And how do they change with monitoring station? So this is the level at Banning Airport. A couple things to note. Sun rises, and what do we see? We start to see an increase in the ozone levels. By about mid-afternoon, the ozone levels peak, and then they tend to drop with time. And if we just look here, the 8-hour NAC air quality standard for ozone is 70 parts per billion. So you can see it's right. Now, if we look at all 5 locations, and I should have these in order from west to east, but so from the west, Long Beach is the most westernly city, followed by LA, Azusa, Paris, and Banning. And I thought I got rid of the lines, but apparently not. So what do we see here? Typically think of LA as having extremely poor air quality. What do you note from this plot? Is LA the worst? No. Okay. Turns out when you look at this in terms of air quality, in terms of ozone levels, LA is not the worst. Now, Long Beach is right here. And if you see the peak for Long Beach and LA are actually about the same time. We can go back and look at our map. We've got Long Beach here and we've got LA here. So this peak occurs about noon and about the same time. Now, if we look then, the next city that's to the west is Azusa. Its peak occurs a little bit later. If we look at Paris, it occurs a little bit later, and Banning is even later. So what's happening? Let's go back to this plot here. What's happening here? Prevailing wind direction from the west, so it's a westerly wind. What's happening? Is ozone a primary or a secondary pollutant?
Secondary.
It's a secondary pollutant, okay? So the primary pollutants are NO, to some extent NO2, and VOCs, volatile organic chemicals. So what's happening? As air is moving, these reactions are occurring. So these chemicals here are reacting. We have sunlight, happens to be a warm day, and then as the air moves, it's generating more ozone. And actually what happens is that air hits that mountain and reflects back. So you end up with this buildup of ozone concentration. Our NOx standard is right here at 70 parts per billion. That's the 8-hour standard. So we have significantly high concentrations of ozone in the more eastern regions. In fact, it's closest to the mountains where we have the highest concentrations of ozone because of these reactions. This is the classic ozone plot where you see an increase, again, as the sun comes up, you see this increase. It's also rush hour in the morning. You see an increase. Often you'll see a peak around noon. You'll often see a peak later in the day, and then the concentration decreases at night, and the same thing occurs over and over again. Plot is from 1979. At that point, the NAC for ozone was 120 parts per billion. As I mentioned, it is now 70. So it's now right in here. So it's now 70. It was decreased from 75 to 70 in 2015. So what's happening? What's happening is that what's being released is predominantly NO, but we also have NO2. It's a combination of reactions where we get NO2 reacting with sunlight. We produce atomic oxygen. That atomic oxygen reacts with molecular oxygen to produce ozone. This is a cyclic reaction. It's quite complicated. We produce aldehydes. This hydrocarbons, as you see, will play a significant role in that. And we produce other oxidants. I'm not going to talk much about all of these oxidants, but we're producing a significant number of these oxidants. So I mentioned, when you saw in that previous photo or cartoon, that NO2 reacts with sunlight. So it forms NO and atomic oxygen. It's a first order reaction, and it is a function of the NO2 concentration, and the rate constant is a function of the solar insolation. So solar insolation is very low at night, increases during the day, reaches a maximum around noon, and then decreases again after that. Now, this atomic oxygen does not react with nitrogen. Now, remember, nitrogen is present in the atmosphere at about 78%. So there's a lot of nitrogen present. But this reaction isn't energetically favorable. On the other hand, the reaction between atomic oxygen and molecular oxygen is. And that results in the formation of oxygen. This is exactly the same reaction that occurs if you were to produce ozone, for instance, for air treatment, water treatment, medical use, etc. Now, this reaction here is a second order reaction. It's first order in both diatomic oxygen N in atomic oxygen. So molecular oxygen and atomic oxygen. Now, the NO that we formed in reaction 1 reacts with ozone to form NO2 and oxygen. And this reaction is a function of temperature. Now, the problem scientists had in understanding this reaction is NO is the primary pollutant that's formed from combustion processes. Okay. So we have combustion processes, power plants, automobiles produce NO. Now, in order to produce NO2, we need ozone. But in order to form ozone, we need NO2. So something was missing. And initially, scientists didn't know what it was that was missing. Because you need this reaction here, but in order for that to happen, you need the ozone, which forms from the atomic oxygen. And if we look at what is referred to as the photostationary state relationship, we can see essentially the same thing. So this first reaction we said was a function of sunlight. The second reaction, or the third reaction in the previous one, is a function of temperature. This first one forms atomic oxygen, which is necessary to form O3, and this reaction depletes. Now, if we plot, this is the initial NO2 over NOx, which is NO2 over NO2 plus NO. And we're looking at the initial ratio. So that's starting ratio. And we can essentially show the same thing here. So for instance, if we look right here at an initial concentration of a ratio, initial NOx concentration of 100. So we have NOx at 100 parts per billion. Okay. And then we look at this ratio. What we see is that in order to form high concentrations of ozone, we need a high concentration of this ratio. So we need NO2. The question was, how did that NO2 form? The missing reaction involved the formation of OH radicals. So there was something missing, as I mentioned. Significant emissions from combustion sources is NO, but we need this high ratio to form sufficient or high concentrations of ozone. The OH radical is hydrogen and oxygen, but that oxygen has an unpaired electron, which makes it highly reactive. We look at hydroxide. This is hydroxide. It is a negative charge, and it is not appreciably reactive. It reacts with H+, but it's not reactive in the way that OH radicals are reactive. OH radicals will react with just about anything. The two missing components in that previous set of reactions are OH radicals and hydrocarbons. And what happens, we go to this reaction here. Okay. Notice here, this atomic oxygen here. this atomic oxygen reacts with water to produce OH radicals. That's what was missing. Okay. And those OH radicals will play an important role in these reactions. And this is a little graphic trying to show you the importance of how all of these species interact. So here's our sunlight reacting with NO2, reacting with oxygen. It's formation of O3. It doesn't show the formation of atomic oxygen. We can form NO. And then here you can see the reactions involving and this is an OH radical. This is not the hydroxide. This is an OH radical. So what happens, as I mentioned, we have this reaction here where oxygen, atomic oxygen, reacts with water to form the OH radical. Now, if we have a hydrocarbon, in this case it's shown as methane, that methane reacts with the OH radical to form a methyl radical. Get a series of reactions. This M is just some species that absorbs energy. But the important thing is notice here. What we form is we form a peroxyl radical here. That peroxyl radical reacts with NO to form NO2. That's how we form NO2. So in order to achieve these higher concentrations of NO2, what we need is we need the OH radical and we need hydrocarbons. Without those, we wouldn't produce ozone. And again, this is just another schematic cartoon, just trying to show this. So these hydrocarbons, in this case, it's shown as non-methyl, but same reaction occurs with methane. But these are primary pollutants. NO is also a primary pollutant. And notice, if we look again at time, we see a peak, typically early afternoon, and our oxidants, in this case, are both ozone and OH radicals. We also form aldehydes, which are also an irritant, and these concentrations then will decrease later in the day. So photochemical smog, it's been problematic for much of, basically since at least the 1950s that we've known about it. And you can see this cartoon from, or this photo from the 50s, where early 60s out in LA, where people are supposedly selling clean air. Now, what we need in order, let me ask you, what do we need in order for photochemical smog to occur?
OH radicals and hydrocarbons.
Okay, so we need the OH radicals are formed. We need hydrocarbons. What else? Think about conditions rather than pollutants.
Sunlight.
Excuse me? Sunlight. Exactly. We need sunlight. We also typically need warmer temperatures. And usually we will have low wind speed and often a slow-moving weather system. We need time for these reactions to occur. May have an inversion, and that inversion is holding these pollutants close to the Earth's surface where they're baking and reacting with the warmer temperatures and the sunlight. Now, in terms of the effect of VOC concentration, we've got initial VOC concentrations. Okay. In much of the US, South Korea, the concentrations of VOCs will be quite low. And this is now. concentrations of VOCs in Santa Catalina, Mexico, been measured to be about 1,000 parts per million. This is parts per million as carbon. So notice if we're in, let's take this region here. If we decrease the VOC concentration, we get a decrease in the ozone concentration. If we increase it, we get an increase, but it's not linear. And if the concentrations of VOC are extremely high, notice increasing, if we go from here to here, I'll call this B prime. If we increase the concentration here from roughly 1,200 parts per billion as carbon to 1,600 parts per billion as carbon, notice there's virtually no difference in the maximum ozone concentration. So at this point, the VOC becomes rate limiting. You don't want to be out in these levels of VOCs, but at these very high VOC concentrations, VOCs do become rate limiting. And we can also look at the effect of NOx concentration. In the US, the 10th to 90th percentile levels for NO2 range from about 32 to 58 parts per billion. So we're right in, this would be 20. So we're right in kind of this range right here. And notice here, if we decrease the NOx concentration, we see a decrease in ozone. If we increase it, we see an increase here. On the other hand, and this is for a VOC concentration of 600 parts per billion, and this is high. This would be quite a contaminated urban environment. These levels, for instance, have been measured in areas, for instance, around our petroleum refineries. So notice here, though, if we look here, if we increase the NOx concentration, what happens to the ozone level? What the 10th to 90th percentile means that if we if we were to measure NO2, when we measure NO2 across the US, so the average is 50th percentile. All of less than 10% of the sites where we measure NO2 will be less than 32 or greater than 58 parts per billion. Okay. So if we look across the entire US at all of the measurements of NO2, less than 10% or 10% will be less than 32, 10% will be greater. So basically everything is within, almost all of your measurements are going to fall within that 32 to 58. It's actually a pretty tight range for NOx concentration. Okay, look at point B. If we're at an initial concentration of 80 parts per billion, and we increase that, what happens to the ozone concentration? It actually decreases, which is counterintuitive. If we decrease NOx, it also decreases ozone. If we're out here at 120 parts per billion, if I increase NOx, it decreases the ozone level. If I decrease the NOx, I actually increase the ozone level. So the relationship between NOx and ozone is extremely complicated. Now, for the most part, we're now down in these regions here, so it's pretty straightforward. But at much higher NOx concentrations, the impact of NOx on ozone levels is not straightforward, which makes control of ozone much more difficult. It's not necessarily straightforward. We can say that in this plot here, where what we will look at is a situation, we're going to start at point A, where the VOC concentration is 600 parts per billion as carbon. The NOx concentration is 100 parts per billion. And under those conditions, the ozone concentration is calculated, and it would be calculated with an extensive, complicated model to be 143 parts per billion. What we want to do is we want to estimate the impact of reducing VOC emissions or reducing NOx emissions on ozone levels, or what happens if we increase those emissions. So we're going to use this ozone isopleth plot. Now, this is from a specific model. It's under specific temperature, solar radiation or insolation. So it is just purely, in this case, it is purely indicative of how these changes would impact ozone levels. So we'll use this, but know that it's for specific conditions and cannot be generalized to across all conditions. So we could not take this data and apply it to Michigan today. But let's look at this. So we start at a VOC concentration. We're starting here. So point A is a VOC concentration of 600 parts per billion as carbon. So this is our VOC concentration. Our NOx concentration is 100 parts per billion. And we're looking at the level of ozone. This is what we're trying to determine from these isopleth lines. So this is the isopleth line for 140. This is 150. We interpolate between those three, and we're going to assume about 143 parts per billion. Okay. If we got a ruler, we could actually even more accurately measure that. So now, what happens if we if we decrease the VOC concentration by 20%? So if we decrease the VOC concentration by 20%, the VOC concentration here, so point, I'm going to change the color. So this orange color is for a VOC concentration of 480 parts per billion carbon. The NOx remains the same. Okay, so that's going to remain the same. So VOC, start here. Okay. We're going to decrease it to about 480. So we're going to decrease it so we're right in about here. Okay. NOx doesn't change. So in this case, we're interpolating between this line here, this 120 line, and the 130 line. And this is about 125 parts per billion. What if we increase the VOC concentration by 20%? So let's change the color again. I'll use purple here. So here, now my VOC concentration will increase by 20%, and this is 720 parts per billion. See, NOx remains the same, still is 100. So now we're out here at a VOC concentration of about 120. We're going to compare. This is the 150 line. This is the 160 line. And that will give us an ozone concentration of about 155. So notice here, increasing for this set of conditions, we increase the ozone concentration. We actually get about an 8% increase in ozone concentration. Under this situation, switch colors again, go back to here, this gave us about a 13% decrease in the ozone concentration. We can similarly look at keeping the VOC concentrations constant, but reducing the NOx. So let's reduce the NOx by 20%. So now we're here. So go back to the original concentration. So our VOC here is 600 parts per billion carbon, but our NOx, we've decreased by 20%, so it's 80 parts per billion. And we're right in about here. So we're between the 140 and the 150. So we have an ozone concentration about 144 parts per billion. And notice here, okay, we see roughly the same concentration. So we've put in the effort to decrease the NOx concentration, but essentially we've got no benefit from it. On the other hand, if we increase the NOx concentration, so we're now up here, right in, okay? So sorry, it should be closer. Apologies, it's more here. So we increase it now by 20%. So let's change the color. So we're going to increase it here. We're right about there. Here. So what's happened now is VOC is the same. Our NOx, we've increased to 120 parts per billion. And now we have an ozone concentration of about 130. So we've actually achieved about a 9% decrease. So the reason I go through this is really so that you have some sense of the complexity of these reactions, that we can't just simply say that a X percentage reduction in VOCs will have a similar percentage reduction in ozone, or the same for NOx. The rule for ozone is extremely complicated. The only thing that you really need to worry about, unless you go into air quality, is that the new rule is a 70 parts per billion 8-hour average. We will talk about non-attainment areas later, but areas are considered non-attainment if they exceed a certain level of the standard. So for instance, designation of extreme means that the level observed in that region is roughly 233% or greater than the standard, than that 70. And they actually have 20 years to try and come into attainment. The attainment or the non-attainment areas in the US are shown here. This is based on the 2015 standard. So you can see there are a number of areas in Michigan, mainly on the western regions. Predominantly, this is because of pollution from Illinois and Indiana. And then we have Detroit. You can see California. California is classified as extreme. So there's significantly higher levels of ozone than the standard. So that's why there's only a few areas that are considered moderate, and you can see those that are also in California, and a few that are serious. But for the most part, you see a number of regions, and these are based on counties, that are non-attainment. We'll talk more about what that actually means. So we'll end there. Hopefully that's helped in terms of understanding what we mean by photochemical smog, and I'm happy to answer any questions.